All right, ladies and gentlemen, we're going to try and do a reasonable job. Excuse me, guys. All right. Here's some of the page numbers and topics that we are going to talk about. So if you pull down the notes for January 12th, you'll see a list, which you probably already copied in your notes, of the major topics that are going to be covered on the test. So I'm just going to kind of rewrite those so we can all get an idea of where we are. Going in the order that I had written before, we had done U-substitutions with a change of variable. That's starting on page 295. Integration by parts. That starts on page 525. And we'll be doing both the infinite and the finite case, or at least be prepared for both. Exponentials. I want to include logarithms in there. Those are covered over a pretty broad range. That's pages 332, 350, and 360. Okay. Those are the starting pages for the units in question. Those aren't the pages that are full of problems, but obviously the pages full of problems are at the end of those units. Volume of revolution. That's on page 467. By the way, I'm talking about the Larson book for all of these, not the blue book, but the gray book. Just a moment. Mean value theorem for both derivatives and integrals. Hey, what's with the mutiny, guys? I'll scroll up in a minute. Riemann Sum, page 271. All right, so we're going to take a look at those. Now, some of the other things that you're going to know about that you already know about the test is that it's 10 problems long, along with a bonus. One of the questions is definitely off of the IB problem set. Okay. And there's definitely room in here to have some overlap. Like there could be an exponential or a logarithm with a volume of revolution, or there could be a U-substitution along with an integration by parts, all in the same problem wrapped together, that kind of thing. Okay. So first, let's go through them in orders, in chronological order. Let's do the mean value theorem. Hop on over to page 172. Okay. And specifically, if we head on into 176, 177. Now, one of the things about the mean value theorem and Rolle's theorem is that it is continuous and differentiable on an interval, a closed interval, AB. Okay, that's an important piece. Now, the answer, C, is an x value in the open interval AB. So what that means is that you can't have a C value be an endpoint. Okay? So if you had a curve that did something like this, and you drew that secant line, those two endpoints are not solutions. Okay? We are looking for another point in that interval that has the same slope. Okay? That's the C you're looking for. Now, as a reminder, what that means is that at that point, C, the slope at C, which is f prime of C, remember f prime is the slope, that's the derivative, at C is the same as the slope between the two endpoints. And we use the slope formula for that. Okay? Where x1 and x2 are really a and b, if you think about it. So let's plug it back in. Well, let's expand it maybe. And written out in more of a formalized fashion, those are the endpoints. So it's still the slope formula on that interval. Okay? That's what the mean value theorem talks about. Right? Now that's the differential formula. So now there's another mean value theorem for integrals. Okay? And the mean value theorem for integrals talks about the average value of an area. The internet's up. Awesome. All right, cool. So the mean value theorem for integrals, I'll make sure I get my formula. The concept there is that you have some interval and I have an area under this curve. And there's a height that corresponds to the average height of this thing. All right? So we can get that formula. My extrema. I don't think that's in that same unit. Hmm. Did we do the mean value theorem for integrals?
Yeah, we did.
I thought. Yeah, oh yeah, it's the whole integral minus the over the average, right? Keep forgetting these things. So this is the integral from a to b of f of x dx 1 over b minus a. Okay. And it basically means that at some particular height, maybe not there, maybe there. If I was, in a sense, to melt all of that into one big block, or if you can think about it, smooth that out, the tops filling in the holes, that kind of thing. So this region here would be equal to those little regions there, okay, where they, right, we're averaging it out into a single block. What's that? Right. That's how it works. Right. Exactly. So it's the average height. Okay. And there are problems that we can definitely do in here. There are problems on page, what do they say? 172. If anybody wants to look at those. And no, Riemann Sum is call it a lower step on the evolutionary scale of an integral. Okay, it's an approximation to an area under a curve. This is not an approximation. This is a full-on integral. Okay, but it's an application of the integral. Okay. You know, like for example, if this was, say, the stock price for over a time interval. Okay. Well, I mean, as those of you who are into the financial markets know, the time scale of stock transactions is small. I mean, we can talk about a stock price over whatever interval you like, whether it be a month, a week, a day, a minute, even a second, or even smaller, because they do really crazy transactions at like microsecond times. But if we were to talk about the variability in that stock price over, say, a minute, this is what it might look like. It might go up, and then it might go down, and it starts at one price, call it whatever f of a is, and ends at whatever price, say, f of b is. Well, the average value of that stock over that minute would be the mean value theorem. Okay, you're finding the average height in that time spot. See what I mean? Okay. If I had to discretize it in a sense, like, give it a single value for that interval, it would be the average value. And this would be how to get the average value. Does that make sense? Okay. I'm talking about that picture right now that you're looking at, the average height. So, anybody want to throw a question out here, or do you want to move on to other stuff? And we'll come back here if you have questions. Yes, I am. All right. Cool. Next. If you guys come up with anything later on, we can always revisit. All right, let's go to Riemann Sums on 271. All right. So what we're doing here is we are finding an approximation for an area under a curve. Okay. Now, as we know, we have a left-hand sum, we have a right-hand sum. So here you can see I'm building a left-handed sum. It's limited by the function on the left. Whereas over here, I'll do, whoops, maybe not. Uh-oh. Okay. That's about enough for me. All right, so here I'm using the left-hand side. Here I'm using a right hand. All right. And depending upon whether your curve is increasing or decreasing, you'll either be overestimating or underestimating. An advantage would be to use the midpoint. And then we have a slightly different formula for how it's done. If you were to do this, yeah, they're basically the same. Where if I was to do, now, the left-handed, if I was to do this on a left-handed version, let's just say, let's make some data, shall we? Now, this data is not for that graph, but it could be a graph. And what we're going to be thinking about is saying, okay, well, first of all, if you can graph it or if you can mentally conceptualize what the graph would look like, and it's not the worst thing in the world if you were on a problem like this to sketch or eyeball sketch what the graph would actually look like. Okay, it's not hard to do. Yeah, they would, because then you're using different methods to solve the problem, and that's one thing that they get excited about. 0, 1, 2, 3, 4, 5. So at 0, I'm at 7, and I'm just going to eyeball this. I don't know where it is or what it looks like, but 6 will be 1, maybe a little less. 2 will be 9. 3 would be 13. 4 would be 18. 5 would be 25. All right, so that's roughly what my picture is going to look like. I don't really need it to be artwork. I just need it to have all the parts. So if we're thinking about a left-hand side, if we were going to do a left-hand one, then my rectangle, my first rectangle, would be a height of 7 and a width of 1. Okay. Then 6 times 1. 9 times 1. 13. And then 18. That's what my left-handed endpoint Riemann sum would look like. Okay. Right, because I'm just summing up all of these little rectangles. Okay. Well, it just depends upon whether you want an overestimation or an underestimation. Okay. And it depends, like, for example, this function goes down and then goes up. So we have a descending region, we have an ascending region. Well, it depends. We have a larger ascending region than we have a descending region.
So if we did a right-hand sum, would you probably overestimate?
A right-hand sum would look like, would probably overestimate, that's right. So if I did that, and I'm just going to try and do this without really jacking the whole thing up. Okay, that's my left-handed limit. And let me see if I can find a different color. It's really hard to see what those colors are, but so a right-handed limit would be those. Okay. Okay. So one of them overestimates, one of them underestimates. Depends upon whether you're increasing, whether you're decreasing. Midpoint is generally more accurate. And the smaller your intervals get, the more accurate they are. Now, we don't have to have evenly spaced intervals. We could have jacked up intervals, okay? Maybe missing data points, that kind of thing, all right? So graphically, it's much easier to put your brain around it. You can remember a formula if you like, and in fact, what's going on with that would be sum of the function at an individual height n intervals times the width of the interval. Okay. Okay. Now, this is, if you look at this and kind of, blur your mental lines a little bit, you can see that this kind of almost looks like an integral. A summation of a function with a change in x. This is where the integral concept begins. Now, if I think about, if I look at this, would this be a left-hand limit or a right-handed limit? Sorry, a left-handed interval or a right-handed Riemann sum? Where does it begin? Left-handed, because it begins at the 0th value, right? The very, very first entry of it all, x equals 0, or whatever the very beginning, the starting interval. If I wanted to make this into a right-hand one, what do you think I might do? What do you think I might change? Yeah, I equals 1 is where it would begin. It would start at the first point rather than at the, sorry, it would start at the second point rather than at the first point. Okay. The width of the interval is irrelevant because I'm saying this ticker, this I equals whatever, is just scrolling through my data points. Okay? This would be x sub 0, x sub 1, and so on and so on and so on. Or rather, I should say, that's x sub 0.
2.5 is
The iterator.
yeah, not it's basically there's that's the second. I guess it's the second axis.
It's the first zeroth, the first, the second, third, so on and so forth. So, and in fact, we can turn this into an integral by making the interval smaller and smaller and smaller and smaller and smaller, which means that basically what we do is we take a limit as delta x goes to 0. And what this does is it goes and we've talked about this, where the interval gets smaller and smaller and smaller and smaller and smaller, and my approximation gets better and better and better until eventually the width of the interval is 0, and I have the integral. Okay. And that's where it all comes from. A Riemann sum is a crude integral. It's kind of like a early precursor to the exact value, which is the integral. Okay. There we go. Yes, it's the freshman version of an integral. There we go. You know, learn how to do baby steps, right? But that's the long and short of how it all begins. So these kinds of data points, which you guys did, you can definitely imagine that there could be a kind of problem, and you should expect some kind of a problem for this. Now, let's just say theoretically that you had a problem set that had a missing data point. Oops. You know, somebody spilled soda on the lab book when that data point was collected, and you want to know what would be a good approximation for that value. The simplest answer is to use a linear regression in a sense. Find the line that connects, the secant line that connects these 2 points, 2 and 4. Okay? And this kind of goes back to this, where I would say to you, find me the line that satisfies the mean value theorem. Or, in this case, use that line to approximate a value at, say, x equals 3. Okay. So if that were the case, one second, if that were the case, we're dealing with 2, 9, 4, 18. And what we want to do is we want to find the line, the secant line that connects those 2 points. Because remember, there is some curve in here, but we don't know what it is. Okay. We just have data points, right? I mean, if you were looking, and I use the example of somebody taking altitude readings in an airplane every couple of minutes or so. Well, if somebody got distracted during the 3rd minute, you would only have the data point at the 2nd minute and at the 4th minute. And you would want to find a good value for the 3rd. Now, the simple answer is to, well, first of all, one thing you could do is what? Since it's right in the middle. Since the data point I'm looking for is right in the middle of 2 and 4, what is a good way to find that answer? Midpoint formula, which is also the same as what? Well, yeah, for the Riemann sum, but I mean, just to find the value that's in the middle of 9 and 18, what do? Take the average, which is the same as the midpoint formula. Remember, the midpoint formula is the average of the x's and the average of the y's. Okay? So the average of 9 and 18 is, right. And what did we say 3 was before? 13, I think. At 3, I think it was 13, yeah. Right, so, you know, it's a loose, easy way of finding that value, okay? But if you didn't have it exactly at 3, and maybe you were looking at it at, say, 2.5, now you're going to have to find a line, okay? So this is the kind of thing that goes back to Algebra 1, but I've seen mistakes be made, and I want to make sure we're good. So the slope would be 18 minus 9 all over 4 minus 2, which is 9 all over 2, or 4.5. That's my slope. Okay. No big excitement there. Now we use the point slope formula. And you can use either data point. Let's just keep it at 9 over 2. X, and we used that, so we'll use 4. And now and we kind of got lucky there. Where my B term is 0, which is just more of a coincidence than anything else. And now if we wanted to find the value at, say, 2.5, we would plug in 2.5. Okay? And that would give me a way to approximate a value in an interval. Yes?
How do we know if there's a hole in the function without using Regression?
What do you mean a hole?
Like, say for example,
Like this example that I'm just talking about now?
yeah, if that was a function.
Well, the data point wouldn't exist, and I would ask you for it. We're talking about a discrete set of data.
No, what if you like asked us for a mean value theorem, but it wasn't continuous? You didn't actually say that it wasn't continuous. Like say for example, you gave us a function that had a hole, and you wanted to mean value.
Well, first of all, if I was designing a question that was intended to fail, then there are certain functions that you should expect are not continuous and do have holes. For example, rational functions have holes, okay, or asymptotes. Things of the form those usually have zeros. I'm sorry, have asymptotes or holes. Other things that often have asymptotes and holes are, inverse functions. Other things that have holes or are non-differentiable are things with rational exponents. Those things often have cusps or weird places where things don't play nice. Okay. Other things would be, for example, absolute value functions. Those are non-continuous. Well, those are continuous. They're just not differentiable. Mm-hmm.
There's also those ones where like it's like x minus something, and then on top it's also it's like where
Write it down on the board because I don't know what you're talking. We got space all around us, so.
Plug in like say an x value and then bottom of 0.
Right, like f of x over g of x. Yeah, rational functions. You've got some polynomial divided by some polynomial. If they factor out, you'll have a hole. If they don't factor, you'll have a 0. Well, sorry, you'll have an asymptote where the denominator is 0. Was that a question or a stretch? Okay. So there are some functions that you should immediately recognize are things that don't play nice. Okay? And if that's the case, you want to look for those holes and see if the holes or asymptotes are in the interval that I care about. Okay? So for example, the function 1 over x is not continuous over the real numbers. It has an asymptote at 0. Vertical asymptote at 0. But if I cared about the interval from 2 to 5, it would be fine. We could do that. That's no problem. From 2 to 5, sure, it's continuous between 2 and 5. It's just not continuous now. Okay? So you're going to have to pay attention to where the possible zeros and holes and things like that, discontinuities exist. Okay? All right. All right. Going chronologically, U-substitutions, change a variable. This is probably one of the places where I have the most freedom to introduce lots of different things. Because U-substitution is one of those tools that is kind of universal. And it's the kind of thing that is, at least in my mind, the first tool in my arsenal when I attempt to take an integral. If I'm trying to find an integral, the first thing I think of is like, can I do a U-substitution? And if so, what would it look like? The next tool in your toolbox is looking for integration by parts, and some of them, and then inverse trig. All right.
First example, we can use the double export produce of the x
So just 9 to the x?
I don't know.
All right.
Yeah, like a double.
If you gave us, I wrote it down like really stupidly.
The pattern you look for this is the general pattern for U-substitution, where you have some function, and inside that inside there we have a derivative of something else. Like, for example, okay, because if you look at this carefully, you'll see that I've got a function and its derivative. And I've got this wrapper function, which is the square root. Okay? This is the kind of idea to look for.
There's no three there. You put up a third.
Right, if I don't have constants, I can always create a constant. Constants are cheap. All right, so we have, there are times, let's do exchange of variables situation. So, all right, x all over the square root of 2x minus 1. Okay. Now, whenever you're doing a U substitution, the entire job is to get something that x equals and something that dx equals. Because if you have something for x and something for dx, then you can get rid of all of your x's and simplify this thing in terms of just u's. Now, if it doesn't get nicer, try something else. If it does get nicer, roll with it. So, for example, let's say u equals 2x minus 1. Now, du is equal to 2 dx. Okay, fine. If I substitute right now, I still don't have anything to play around with the x up top. That's where the magic lies. So we're going to solve for x. And we're going to solve for dx. And now when we make our substitutions, we'll get it all just in terms of u's. So this becomes okay, just making a whole bunch of straight substitutions before I simplify, which you'll see comes out. All right. All I did was substitute. Dx is equal to 1/2 du. Okay. Now I can go ahead and simplify this, clean this up, yeah, blah, 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 and we'll see what we get. So this becomes, let's fool with the top in a minute. This thing, as you can see, turns into the square root of u. My 1/2 comes out. So all I really did was play with the denominator and the 1/2 in front of the du. And now we can go ahead and clean that up a little bit more. Pull that 1/2 out. Okay. And the beautiful part about this now is that I have a single item in my denominator. And even though I've got more than one term in my numerator, who cares? I can split up my fraction. Okay. Yeah.
You can go from the numerator be u plus 1 over 2 to just u plus 1 in the square root.
In this step, from here to there, and then when I pull it outside, it becomes 1/4. Yes? Yes? Happy, happy. All right, now, clean this up, integrate, move on with life. Integrating them. -2 over 3. Oh no, positive, I'm sorry. I was taking a derivative. Not du anymore, sorry, plus c. And you can clean that up a little bit, or you can remake your insert your substitution. Remember what u was 2x plus 1, minus 1, thank you. If you left it like that, I would probably be okay. Or you can go ahead and find your common denominators and all and rationalize denominators and waste a whole lot of time, or leave it like that and I'll be fine.
You take the integral of u to the 1/2 half, doesn't it become 3 over 2?
Hmm?
It's like,
You didn't
at the up
increase it by
top.
1.
I took the derivative. Where's my brain? Gosh, I'm having the morning, aren't I? This is u to the 1/2, and when I integrate it, it becomes u to the 3/2 times the constant 2 over 3. And now when I simplify, I get 1 over 6. And of course, you can simplify this a little further. I'm not really particularly interested in making it into its nice, happy form. We have other things to solve. Okay?
So you see what I'm saying?
No.
You know, it's like 3 to the n squared.
So you're talking about 9 to the a.
But isn't it like a squared? So you can bring the down.
Exponents are commutative as long as the base is positive.
Okay, because we have like an example in the notes. Where it's like the integral of 3 to the x to the squared times x. And then you gave us.
Yeah, we'll get to the exponents and logarithms in a little bit. But as long as the base of your number is positive number, or non-zero, it's a positive number, then exponents are commutative.
Okay. So I can just bring the squared.
Yeah, if it was a positive 3. If it was a negative 3, doesn't fly like that anymore. Okay. We didn't go too far into even and odds. We'll probably hit that up later just for giggles. Exponentials, 332, 350, 360. So for example, example 2, page 332, is a good problem. Okay, integral of 1 over 4x minus 1. All right. So if we do a U-substitution, and at this point, you really don't even need to do a complete change of variable, but you should realize that dx is equal to 1/4 du, which means I got to put that 1/4 in there somehow. That 1/4 has to be in the game. So this becomes the integral of 1 over u, and dx is 1/4 du. Okay? So straight substitutions are really nice. Sometimes they definitely clean up the problem, and we wind up with something not so bad. All right, now doing this is the straight logarithm, natural log rather, of u. But because u is a function that could be negative, okay, we don't want u to be a negative number. We can't allow a negative number. Because the natural log doesn't fly for non-positive things. Can't work for 0, and it can't work for negatives. That's why you'll see bars on it. Absolute value bars. There are some u's, however, that are always positive things. For example, x squared is always a positive thing. or the square root is always a positive thing. Okay. Yeah. Other things that are always positive. Any any even power could possibly always be positive unless it was, unless it had roots. Anything that doesn't have roots you don't have to put the bars on. But anything that has a root, you have to put a bar on. Okay. And now you resubstitute. And then you're done. Okay.
How do I know when to take the log and when to take the natural log?
You can always use the natural log. The natural log is always a nice one to play with. Because the derivative of the natural log is 1 over the function inside it. You won't have, the only time that you would come up with an answer that is like log base 7 or whatever is if you did it with the natural log and then use the change of base formula to turn it into log base 7.
Okay, so basically natural log is...
Natural log is the flavor of the day, yeah. Let the record know it is currently 8:31 and Harold has graced us with his presence. How nice. Now, so for example, if you have other crazy bases, okay, don't need to worry about it. I gave 3 values for those. So 332, 350, 360. We didn't worry too much about slope fields, but we will later. All right, so exponential equations. Let's do number 90 on page 358. E to the 2x, 1 plus e to the 2x. So what's the first thing you think about? Yeah, U-substitution is a good place to start. Well, which would you prefer to use? What is your U going to be? Just e to the 2x? You see, yeah, you can throw in the 1 plus e to the 2x because when you take the derivative of it, the 1 is going to go away. Okay? You could do it either way. All roads will lead to Rome, unless you're pointing away from Rome. So now du would be e to the 2x times the derivative of 2x, which is just 2. Okay? Now, if we look at this, this is my u. And as soon as I throw in a 2, that will be my du. Okay, I have to give it a 2, which means I have to put a 1/2 out in front. Okay? So I plug in a 2, and I put a 1/2 out in front. You wind up with 1/2 the integral of 1 over u du, which is the natural log. Now, What about the absolute value bars? Do I need the absolute value bars for this guy? Can e to the 2x ever become a negative? The exponential function, does it ever go negative? No, it doesn't. The exponential function, like that, right, is always a positive thing. So, unless I subtracted a number from it, but I'm adding one to it, so we don't have to worry. And now I have the natural log of u plus c, and plugging u back in, and there we have it.
Can I put the absolute value around it at all times? Because then
Wouldn't hurt.
unstate.
Yeah, but I'll tell you that it might complicate things. Like, for example, if I made my u e to the 2x, so that when I resubstituted, the log and the natural log would cancel. With the bars in there, you can't immediately cancel. You have to split the function up into two parts. See what I mean? It's pretty much often safe. But if I did use u to be just e to the 2x, it comes out slightly different, but it always works out. So let's do that just for giggles. If I set u equals e to the 2x, du would be equal to e to the 2x times 2 times dx. So now this becomes, well, again, I have my 1/2 that I have to throw in there. And I get my du, and now this becomes 1 plus u. And now this is the natural log and resubstituting and I get the same thing. So it didn't really matter what I used, as long as I didn't break a rule. Okay. All right, now when you have bases that are not E, okay, slightly different. Those are differentials. Sure. Okay. All right. Let's see where all this comes from. So let's just say I have the integral of 3 to the x dx. All right. So let's say that without knowing what we're doing, say you totally forgot, no idea how to do this, completely forgot what the simple formula is for bases other than E. Well, let's say u is equal to 3 to the x. Now let's solve for x and see what we get. Well, first of all, the derivative of this, okay, the derivative of u, du, would be 3 to the x times the natural log of 3, okay, times the derivative of x, which is 1 in this case. I mean, if that was x squared, then I would have to put a 2x there, I mean, it's always the derivative. It's the chain rule. You're always taking the derivative of the outer wrapper, which is 3 to the something, and then the inner wrapper, which is f of x, whatever that guy is. So, dx. All right. Now, I've got my u. This is u. Now I got to get rid of dx. Got to find a way to get rid of dx. So I'm going to look at dx, and I'm going to say, let's solve for dx and see what I actually get, okay? Well, I've got this and I've got that already in my integral. So all I really have to do is get rid of the natural log of 3, and I'm set. So I do 1 all over the natural log of 3 du is equal to 3 to the x dx. Now, the natural log of 3 is just a number. Okay, the natural log of 3 is, 2 point something small. Okay. So this whole thing becomes the integral of 1 all over the natural log of 3 du, which comes out in front and now I resubstitute for u, and I'm done. So even if you lose all the shortcuts,
Please pardon this interruption. SMS is up and running. Teachers, please take attendance in SMS. Thank you.
so I'm going to wait a few minutes because everyone and their brother's logging on, and they're going to crash the system again. So the shortcut idea is that when I have a base other than e, I am going to have to put that 1 all over the natural log of that base outside. Okay. But if you totally forget, if you completely forget all of the shortcut rules, first of all, you've got a formula sheet. Okay. But even if you totally forget, U-substitution goes really far. Okay. So if you look at page 366 or 367, you'll see plenty of examples, including the one I just put on the board. Anybody want to look at any in particular? Log base 3 of that mess. Okay, sure. You just finding the derivative? Log of funky bases. Got to remember the base, the change of base formula. Log base m all over to the a is equal to log base n of a all over log base n of m. Okay, now usually we pick the natural log to be the log base n, whatever n is. I mean, whatever's going on. So for example, if I have this, log base 3 of f of x, okay, this is my function and I'm asked to play with it and I want to get it into natural log form, which is easier to fool with, you can turn this into the natural log of f of x all over the natural log of 3. Now we like natural logs because it doesn't involve other steps. I mean, the derivative of natural log is 1 over the function. Okay. The integral of the natural log is a little bit weirder. That's x natural log of f of x minus x, which everyone remembers. Right.
Yeah.
Sure. Me too. But this is a way to turn your stuff into something a little bit more normal. Okay. So for example, if you wanted to fool around with number 44, what do we got there? X squared root of 1 minus x minus 1 all over 2. minus or plus? Minus. All right, this is number 44 on 366. Number 44. So, oh, I'm sorry, there was a log in front of it. Log base 3 of that whole thing. Okay, well, when I deal with this, we can use some log rules to make our life a little easier right away. Okay. Okay, that right away allows me to throw away the 1/2. Okay, because if I'm taking a derivative of that constant, it goes away. So I can just use my log rules and ignore it. Okay. Okay. Some of you might be saying, well, can't I turn that log into a product, which becomes a sum, and then, yeah, but you know what? The problem is that as soon as I do that, sure, I can split it up. But first of all, we haven't dealt with the log base 3 part yet. But even when we do split that guy up, you're going to get a log base 3, and you're going to get a log base 3 of x, and you're going to log base 3 of x minus 1. And we can't split up x minus 1. So it's probably just as well to deal with it right now. You can try, but you'll be facing away from Rome. So I use my change of base formula. Sorry. And now I can use the product rule. Or in fact, the chain rule and the product rule. So the derivative of the natural log is 1 all over whatever's inside times the derivative of what's inside. And if we take the derivative of what's inside, we have to use the product rule. So product rule says U, V, so that's U prime V, V, U prime, U prime, which is x, which is 1, so now we've got the square root of x minus 1, plus x all over 2 square roots of x minus 1. It's a constant. You know, the natural log of 3 is just a number. It's just a constant. It comes out, right? You're not fooling with it. And in fact, this thing cleans up pretty nicely if we actually multiply and distribute in. Distributing in, these radicals disappear. And those x's cancel out, and I wind up with and, you know, you can simplify if you really want to. It's no problem. So I get 2x minus 2 plus x. And that's probably good enough for me. I probably would have settled with three lines above it, but as long as you did that product rule, I'd probably be fine. Yeah. If you stopped here, I'd be fine. You don't have to go so far. I don't need you to spend time cleaning it up. I want you to get into a form that is acceptable, that, after you've taken derivatives and product rules and quotient rules and chain rules and all that stuff, we don't need to clean up and do exercises in algebra. All right? Mm-hmm. Yeah, you know how to do the steps. All right, those are my exponentials. Volumes of revolution, that's pretty much fresh in our minds, I hope. Volume of revolution, that's 467. The whole idea with a volume of revolution and this comes from the concept of pi r squared. Okay. Now, what that r is depends upon the function and what you're revolving around. Okay. And this thing could be written in terms of revolving around x or revolving around y. We're definitely going to have bounds, a and b. Okay. So, for example, if I had, let's do the function square root of x plus 2 dx. Now this, I'm going to change that to, let's keep it at x plus 2. That's fine. X plus 2. But we'll revolve it around x equals negative 3. Okay, that's what we're going to revolve it around. Now, we are going to have to play with this because we have to, and let's integrate between, say, negative 2 and 2. And that's the window that we're going to integrate around. All right. All right, so what is a good thing to do is to sketch this function, just like I did. Okay, you can eyeball that. You know where these things are. You've done transformations. You know what that function looks like. Okay, and then think to yourself, what is the radius? The radius that we're spinning around is that. Okay, when this thing spins, if you were to think about this guy spinning, it's going to give me some weird-looking funnel idea. You see how that looks? All right. And then the radius of that funnel is going to be that, whatever the heck that is. Now, that is, you're starting at -3 and you're going to the function at a value, okay? So we have, my radius is going to be at 0, -2. So it's going to be x minus, sorry, -3 minus the square root of x minus 2 plus 2. Wait, I'm backwards. And it's always a good idea to check, all right? At -2, this right? Yeah, you see, this is a good way to check. You gotta make sure that you're playing it right. At -2, my radius had better be 1. Well, it's not here. At 2, it should be 5, right? Yeah, that's it. Minus a -3. Where's my function? F of x, which is, it's basically what we're doing is we're shifting it over by 1. That's correct. It's not. Where's my? Okay, just let me use my cheat sheet. Yeah. Oh, you know why I'm having a problem with it? Yeah, because I'm revolving it about, this looks like I'm revolving it about y, so we have to change my function. That's why I'm having an issue. Y equals the square root, no wonder, x minus 2 plus 2, which goes to y squared minus 2 equals x. Right? Okay. We have flex. I'll see you then. No. Okay, so let's just get back to this real fast. And one thing, as you remember, I got twisted up on this one. And what I really ought to have done was just thought up to myself, how do I find the distance between 2 points on a number line? Because that's really all we're dealing with. I mean, if we have some value a, or let's just call it x2, and I have this other value x1, and I was thinking about the distance between them, because that's really what you're talking about. In this case, you have -3, and then you have the function's value. Okay? And so if we think about the distance between those, it's the outer minus the inner. So it's going to be this function minus the interior function. Okay? So we have outer minus inner. Okay? I don't understand the question. This length. The length from there to there. Okay, is the radius of that disk. If you think about this disk. Okay? That guy's radius, if at 2, the radius would be 5. Right? And at -2, it would be 1. So if I plug in now the height at 2 is there. Okay. So at at 2, the height is 2, right? So that would be 2 squared, which is 4, minus 2, which is 2, plus 3, which is 5. So this one actually works. Okay. So when we set up our integral, our y bounds are from 0 to 2. We're going that height up. See, that's what we're integrating. We're integrating over that area from 0 to 2 of my function. Or really just y squared plus 1 dx, dy. And now we're spinning that, so we square it, and we put a pi on it. And I leave the integral to you. Now, if we were revolving the same volume over the x-axis, or rather some other x value, we'll go into that in a second. No. I'm revolving around a vertical line. You see? So the area that I'm really interested in is this area. See?
But earlier we said like downward from -2 to 2.
Right, because we express the function in terms of x. Now, if I was spinning about the x-axis, which I'm about to do, then my bounds would be from -2 to 2, because that would be a different area. I would be integrating that area, which is a different integral. Okay. So if I'm at and now I'm about the x-axis. Or rather, let's do about y equals 5. Okay, about the line y equals 5. So x plus 2 looks like that. Okay, and my bounds are going to be from -2 to 2. So this is the area that I'm interested in. Actually, I'm lying. That would be if I was revolving around the x-axis, but I'm not. Instead, the area that I'm interested in is revolving about the line y equals 5, which is up here. So the area that I'm really integrating around it's this object that's being spun about the line y equals x, about the line y equals 5. See? That's really what's being spun, if you think about it. Okay? Yes? So, now I have to consider what is my radius. A radius is going to be that piece right there. That's the radius that I'm spinning. Okay? Right? Okay. So, I have the outer, this is my outer, and inner. Okay? So it's going to be the function x plus 2 minus 5. Whoops. No. Wait, yes. Yes. No, we should be the other way around. From yeah, you see again. No, you see now we're spinning. Yeah, this is fine. And yeah, at 2 it would at the height at 2 would be the square root of 2. And right? At 2 it's 2. Right. Yeah, at 2 it's 2. So that means that distance would be 3. Right, so I'm good. And now I just square it and throw a pi on it. And we have to go from -2 to 2. Yeah.
So how do we know if it's like a donut shape and there's a
Okay. The area between two curves spun. So for example, if I had find the area between x to the third minus 2 and y equals x, And we're going to revolve this guy about y equals -1. Okay. Yes. First thing we got to do is think about what this graph looks like. It's going to look like that. Actually, I don't want to have it spun around a line throughout itself. So let's just say yuck. It's going to be ugly. Let's revolve it around the line y equals -1. I'm sorry, between line equals -1 and the x-axis. And we're going to revolve around y equals 2. So we're talking about this region right here. So here's -2, there's -1, 0, and 2. Okay. So we need to find the bounds of that integral. You know, my left bound is x equals 0, but with the right hand bound we have to find. So equals y, and y equals -1. So now x to the third equals 1, adding 2 to both sides. So x is equal to 1. So you had to find the points where the thing intersected. All right. And now we take that and we spin it about so what we have is we have this wedge that's being spun, so that what we have kind of is, in mechanical terms, this is what's called a collet. If you can imagine something almost like a dog's bowl, but without a bottom. Okay. Almost, but it has straight walls. If I was to take a cross section of this, if I was to take a cutting plane and slice it, I would have that's what it would look like if I sliced through it. Okay. So now we set up the integral. So we have an outer radius, which is a solid, if you can think about a dog dish full of concrete, I mean, you know, a disc, a thick, heavy disc. And then what we're going to do is we're going to chop out the inner piece of it all. See, we're starting off with the outer piece. Which looks kind of like that. It's like a solid disc. And then we chop out the middle piece. So to do that, we set up two integrals. The outer disk, which is x cubed minus 2 and it's going from -2 to, from 0 to 1. And I'm going to subtract off the inner disk. And the inner disk is y equals -1. To find the points of intersection. You got to find the places where they intersect so I know the bounds of my integral. All right. Done. Oh, wait, careful. Wait, I'm spinning it around y equals 2. Yeah, so I have to be careful. Yeah, watch out. So and I'm spinning it about 2. So that's 2 minus third. Oops. And the outer, which was 2, minus and if we think about that, that actually that we can verify that with common sense because the inner disk, that hole that I'm punching out, has a radius of 3. Think about it. My axis of y equals 2 is right there. That's what I'm spinning around. And this farthest point of the inner disk is at y equals -1. So that radius should be a radius of 3. So when we come back here, this becomes a radius of 3. And it's a cylinder, pi r squared. And the radius is 3. So that part makes sense. At least it should.
So if you're revolving around the x-axis, then it would be like 2 minus the function. But if you're revolving it around the y-axis, it's the function.
It depends upon whether or not you're spinning below the curve or above the curve. Okay, is your axis above you or is your axis below you? But in fact, it won't matter because you're squaring it anyway. So who cares what order you do it in? Right, as long as you don't have gum in class. Right, yeah. Moving on. I'm not about to go through and have you do all sorts of integrals. I want to know that you can integrate, and I'm going to ask you those questions, but then there will be some questions which will say, set up, don't solve. Or maybe even, which of these is the proper setup for whatever. Oh, don't think I can make a multiple choice question hard. I can make a true-false question hard.
I have faith in
Yeah, I know, yeah.
you. No.
Yeah.
I'm not saying it will be hard. How hard? Insulting.
Integration by parts.
Yay.
All right, last thing. Page 525. Okay. You have U excuse me, uv minus the integral of v du. Okay, u du v dv. Gotcha. Those are the two integrals. We've done a lot of these. Show of hands, who's comfortable? Okay. If you have the finite case where one of your two integrals is going to eventually disappear, okay? You might want to take, you've only got about 8 minutes left of class, right? So, your stuff. You can use the table method for things that will eventually disappear, where I differentiate and I integrate, and I start +1, -1, +1, -1. So we have something here, here, here. So that's the whole basic idea, is that looking at the red lines, you can see what things get grouped together. Okay, so we differentiate over and over and over again, we integrate over and over and over again, and we combine all of my terms. Okay, now remember, if you have something that is infinite, okay, where it eventually becomes itself again, all right, something like, sine of x times e to the x dx. Okay? This thing is going to eventually cycle and become itself again. Okay? You cannot use the table on this guy. You must do this one by hand. But eventually it comes back to itself. Okay? So, for example, if I do this, derivative of sine e to the x, e to the x, and now doing the integral by parts, I get sine x e to the x minus cosine of x e to the x dx. And now we do it again. Cosine of x, derivative of cosine is negative sine of x, e to the x, e to the x. And this becomes e to the x cosine of x minus the integral of negative sine x e to the x dx. Okay? And we simplify. And we notice that we have cycled back to ourselves again. We have the same integral that we started with. So by integrating, we spit out some terms, and then we wind up with ourself again. So what we can do, actually, I dropped a negative sign. Those two negatives become a positive, and that one becomes a negative. So now we're good. Okay. Now what we do is we say, hey, I'm close to where I started. In fact, I am where I started. And we we say, all right, I'm going to combine my like terms. So I bring that integral on the right over to the left. And say, well, I've got two of them now. Divide by 2. I'm going to factor out a GCD because I can. And you're done. So that's the infinite case. Okay. This one only cycled 2 times. You could have it cycle more. Okay. When you do those integrals, you might be spitting out terms and whatnot, coefficients and things. Okay. Be aware of that. Remember that if I have when I integrate that, okay, what do I have really? What I'm saying is that let's say u is equal to e to the x over 2. Well, du is equal to e to the x over 2 times the derivative of x over 2. Okay, which means 2 du is equal to e to the x over 2 dx. So this just becomes 2 du, which is 2u, and then I substitute, and I'm done, plus c. Right? Okay, so pray for snow, an extra day of studying. These notes will be posted and the video will be up this afternoon. If you have questions, shoot me an email. If you're running into problems, if you're practicing on these pages and you say to me, hey, Ronco, I don't get the answer that's in the back of the book, email me and I will be happy to direct you astray. I mean, on the right track. All right. This episode of The Ronco Show has been brought to you by Snowmageddon.